There we go. Hey guys, nice meeting you, and thanks for the introduction, and thanks for the speakers before me, because they gave me quite some footage. So I'm from Chilas. Chilas is a fairly new company, I must say. We spun out of Lionix International in 2018, and at the end of 2018. And well, we have the main office in Eindhoven and the laboratory space here in Enschede, close to our close collaborations, our neighbors, Lionix International, where we get our silicon nitride chips from, and very close to Fix Photonic Assembly, where they do our high volume, fully automatic assembly of our laser systems. And we've got Quicks around the corner, which always have intriguing questions to us, how to make the laser more neat and for the application. So yeah, this is basically our ecosystem here in Enschede. And yeah, well, we commercialize ultra narrow line with external cavity lasers. So as explained by the previous presenters, is that they got a small indium phosphide gain section, which has the advantage of generating a lot of light. And we've got silicon nitride, which has very low losses. And well, when combining these two effects, you get a very nice laser systems. And so the indium phosphide provides the high output power, and the silicon nitride, due to its low loss and the ability to tune some sections on the platform, we can make filter circuits which are based on two rings which are set in Vignette, and I'll demonstrate a little bit about this. Is that we can tune the laser wavelength feedback to the gain section throughout the full C-band and even beyond there. So yeah, the product is very simple, although I must say the thing it does, the fairly high output power and the narrow line width is giving rise for many very complex applications which we can drive the system with. So the gain section is butt coupled to the external cavity. And well, these are already explained. We have the two rings that make the laser tune to basically any wavelength you want to address. We've got several products, few standard products. We've got a fixed wavelength application. It is tunable, but it's specialized for driving one laser at low power consumption. And we've got a tunable application, which has C-band, which I will show you in the next slide, that we can also go far beyond that C-band application. And we have a piece of electronic driver, which yeah, really takes the best out of this laser concerning high output power and tunability and the low noise. The lasers are very sensitive to electronic noise, and I must say there's a lot of development going on in making the electronics, driving electronics, as low noise as possible. Meanwhile, we're also making a piece of software, a tuning software that fully automatically controls the lasers. All the lasers need to be calibrated to fully exploit this feature, and this is typically what a consumer would love to see: is two buttons, one button power and the other one wavelength. And yeah, we're developing that the product for the customers. Yeah, here are some specifications, some specs that we reach. I start with the boring parts, that the side mode suppression of other modes, laser modes or spontaneous emission modes are super suppressed. So we've got a side mode suppression ratio of more than 50 dBs. Relative intensity noise is also super low, thanks to the larger cavity, and yeah, so the laser is super stable and yeah, super pure light. We can tune it. So in this example, from 1480 to 1600 nanometers, and around this wavelength band, it gives a fair output power of yeah, up to 40 milliwatts. And I think this is yeah, driving a lot of application. Most recent developments are concerning, together with scientists making electronics for feedback. in France, and they measured the line width of our laser, which is approximately 4 kilohertz, or even sometimes a bit lower, depends on the electronics and the cavity. And they managed by using a feedback mechanism to suppress the phase even further to record low. And I hope to publish these results soon. And yeah, a little bit of development in the far future or near future, I must say. Things go very fast. So I would like to extend the SCL band a little bit beyond the 1600 nanometers in half a year from now. At the moment, we go up to 1600 nanometers, but next run is in progress right now. So I hope to go beyond that level. Near infrared lasers are currently in the lab operational. Visible lasers have been demonstrated, and yeah, thanks to the silicon nitride, which is transparent for all these wavelengths, give us a gain section, and we'll make the appropriate cavity for it. So that's the strength of this platform. In mid-2020, I hope to have lasers in a compact 14 pence butterfly housing available with 2 gain sections. We expect to have a little bit more than 100 milliwatts of output power in the fiber. And well, I think we can squeeze a little bit more power out of these devices. We will see in the real time. So I hope in a few months to have it on the website. And yeah, on top of that, we have some devices where we have some structures where we can track the wavelength, so you can get feedback from the laser to see at which wavelength it is. And yeah, it's always nice to have for some OEM applications. Well, and now, as I highlighted, any wavelength on demand. Give us a gain section, and then we'll go. And if you don't have a gain section, we will find some gain sections there. Yeah, as explained, the applications are for a wide range of applications: fiber sensors, LiDAR, of course, coherent communication, OCT, microwave photonics, spectroscopy, atom cooling, quantum computation. All these applications now pop up, and they all need specialized, high pure wavelength laser sources. And I think we can do that for all these applications. This is our presentation in a nutshell. Open for any questions. Thank you for your attention.
Thank you, Dimitri. Thank you for a great talk. And yeah, I mean, these results are very impressive. Actually, I have a question. Do you see any room for improvement, for further improvement? And with regards to that, can EPIC members do something for you?
Yeah, so improvement is always there. As indicated, is that the line width is narrow, but you need very low noise electronics to really exploit that. One of my colleagues at Lyonix told me it's like a race motorcycle, but sometimes the driver is drunk, and that's what we now do with internal referencing. I think in a year from now we should have an internal reference, a gas cell, something like that, implemented into the gold box, and then we can make the driver not drunk anymore and really have very nice performance of the laser. The output powers, yes, 100 milliwatts. If it's 300, people are getting more happy with that. And what we would like from the EPIC members is that, especially in this hybrid integration, what we're discussing here, is that we would like to currently put on photodetectors for biasing and monitoring, but it would be nice to also have some feedback directly on the chip to the laser performance itself, to trim the wavelength or stabilize the wavelength, and also to expand the colors and the bands. We see that, yeah, in the world people are presenting silicon nitride structures that can even go beyond the wavelength ranges I just presented, and there we need just gain sections providing a wider range, or perhaps multiple gain section arrays that can be flip chipped with the transfer printing, which has been discussed here. So this is definitely something where we need EPIC members. We can't do it all by ourselves. So yes,